Hello, everyone. This is Brian Cutler. I'm a system engineer with Rosys, and this is the second video of my series of videos to show how to make a in-class example in these process control systems for my guest lecture for NC State's process controls class on Friday, October 23rd. And so in our first video, we figured out how to set up our Studio 5000 program along with the virtual controller that's going to simulate our program. So what in between now and then what I've done is I went ahead and brought in these are called add-on instructions, which they're just Rockwell standard objects that represent control. They're called control modules, which are soft representations of the instruments within the field, like the temperature probes, the valves, the controllers, the controller loops. All those can be represented by these control modules. And these Rockwell standard objects, we could make our own kind of set of objects, but it's really useful from one product to the next that it uses a consistent set of objects, because then that way it saves us some development time, and also we know exactly how they're going to function, which is a large benefit. And if any of you guys are familiar with programming, is that you can think of these as separate functions, and that you just put in different inputs into them, and they spit out outputs, and we can use that within our process control system. So I brought in a analog input AOI, PID block AOI, and a PVALC AOI, and that's because we are going to be making this little system, which is, I'm sure you guys are familiar with seeing these type of drawings within your process controls class. At least the chemical engineering students I know are. Pretty basic control loop, nothing too wild going on. So I just kind of want to show you guys kind of the lowest level of what can be involved in these process control systems. So we got a temperature transmitter on a heat exchanger, again linked to a temperature controller loop being linked back to a steam control valve. So that is what we are going to set up in this system. So the first step, now that we have our add-on instructions brought in, we can go ahead and make our control modules. So the first thing we want to do is make controller tags for those, specifying with the add-on instructions. So I went ahead and already did that. I call them TIC401, TT401, and TV401. And it's as simple as just you type in the name, you call this test, and then you specify the type of data type you want it to be. It could be it doesn't have to be just these add-on instruction data types. That's just because we're making them as control modules. Like if we wanted to we'll go ahead and make a start sim bit. That would be a Boolean bit, which is a true and false bit. And we'll use this later in the program to just turn our sim system on and off. So we'll go ahead and make that now. So we made our controller tags, and then I made a new task called control modules with a program called control modules. And then there's a main routine, which is this is actually the only routine that will be evaluated by the controller within this program. However, how I've been taught to organize my programs, and I think this is that for this you actually just want to keep your main routines pretty lean, and I just have it set up to, they call these JSRs, jump to subroutines, which just tells this main routine to say, hey, also go evaluate this routine along with this routine and this routine. That way you can kind of separate your logic more, and it can be a lot more simple, which is there's a lot of value in that. It can get pretty messy pretty quick. So let's go ahead and look at the temperature probe control module I set up. So we went ahead and put in this add-on instruction block where you can see we specified as TT401, and then that one has always associated parameters. So it has input PV, which is the field value coming from it. So it'd be a 4 to 20 milliamp signal, might be 12 milliamps at a time, or 8 milliamps and so forth. And then this block just scales it linearly from whatever you set your limits to. I set them to 0 to 100 degrees Celsius. So if this was reading in 12 milliamps, it would be a 50 degrees Celsius value within value. And this block down here, I AFI'd it, which stands for always false instruction. So it's pretty much when the code actually goes live, it won't evaluate it, because this is I made 2 I/O modules just as examples. This is an analog input module, and then this is an analog output module, which is if this was a real system and we were actually running copper wires out to these temperature probes and control valves. The temperature probe, the input value to the PLC would actually get landed in a specific slot and channel. So this is slot 3, and then I specify this as slot 3 channel 0. So it would take that input and then push it to this input PV, which then will run it through this add-on instruction, and then it would return the value, which is what we would be using in our process control. Or if you had an HMI, that's what it would be displayed in, or a historian server, that's the value we want to capture for that historian. So moving on to the control valve. So the similar thing, we got a P valve C add-on instruction here with TV401. And once again, we have our analog input from the field, which is showing us the position feedback of the valve. Might be showing us at 25% open or 30% and so forth. And then we have the analog output being sent out to the output module. So what that's saying there is that this, I'll go into this detail with the PID block, but pretty much this PID block will be set up to, I'll just go ahead and show you now. But this temperature value is going to be fed as the input PV to this PID block. This automatically, based upon the configuration setup that we'll set it to, it will automatically do all of those Laplace transforms and whatnot and calculate the control value that we need to set for that flow valve. So that's what this is sitting here. This is saying P set CB. This is saying if it's in program mode, which it will be once we set up our sim logic. If it's in program mode, which in program mode just means that the controller is in control of that valve, because you could have it in operator mode, which is you let even if we tell it to open to 100% from the controller, it's not going to do it. Only the operators can either manually open it or they can send HMI commands to open it. So then we go ahead and, so this was taking the temperature valve, and based on how we configure this PID block, it sends a set point to that P valve C. And then, so then this P valve C gets that set point, and then it says, hey, maybe I'm at 25% open right now, and we just got a set point of 50%. So then that will update this out CB to send a 12 milliamp analog output signal to the control valve, which will then open to that position. So that is pretty much all I'm probably really going to show you guys for this part of the demo. It's just setting up our control modules is kind of our first step in this. I guess one thing you guys are probably interested in, maybe I shouldn't be showing this so you can check your work easily, but let's go ahead and change the controller, the tag scope to PID, and I went ahead and threw random numbers into here as the definition to our temperature controller. So I set our P gain to 2, our integral gain to 1, and derivative gain to 0.2. So we'll use those parameters to control that control loop. So normally it takes a little bit more refinement and a little more intimate understanding that process to know what to set these to, but we're kind of going in blind, so I just kind of set them to random values. So I'm kind of curious to see how this works out. So that pretty much wraps up our second video, and check back in for the third one to see how it all comes together.